is up there. This is Unit 6. The test is open from January 18th to January 24th. Make sure you have a time off during that time to take it. That's the only time it will be open. We're going to be doing gas laws and kinetics. Next time we'll be doing 2 labs. The Graham's law I'll do back in the back with you. It's going to have concentrated hydrochloric acid and ammonium hydroxide. So you need to make sure you're real careful. If you're wearing contacts, you need to make sure that you do the full goggles that go tight to your face on this one. Then we'll do the molar volume of the gas the next time. We'll talk about phase changes and states and change, and then we'll do a heat curve with problems and a heat curve lab the next time, and your lab notebook will be due that day. So it goes on this term, okay? Also, sapling up through 6.4 and quizzes up through 6.4 are due by the 12th. Okay, the other ones will be due on next term. The way that this works, we needed to have it go over those few days. So if we don't cover all the things that we need, we can still use those next days to do that. We'll come back to review day and 6.6 and 6.5 on sapling, and then another review day, and then we'll start the next unit. So that we'll have a couple days of cleanup, and if you need help doing your pre-test, you can get that help that you need there. Okay, any questions with what's going on? I did open up the family quiz one more day because a lot of kids forgot over the break. So it's open today only. So if you want to retake it, I did give you more time to do it. Rather than 30 minutes, I gave you 60. So if you want to retake it, you can. Okay? All right, so moving on. We are going on to kinetics. This to me is the most useful unit for regular life because it has to do with things that we're going to be using in life. So the first thing we're going to do is we're actually going to do some research on something that happened in the community. That happened with gases in our community a couple years ago. Phosphine gas actually killed 2 young children in our neighborhood here in Layton. Some questions I want you to think about while you're researching this is, could this have been avoided? Has anything like this happened before? So as you're doing your research, see if there's anything that's like that that's happened before. I thought there was one more question. No. Okay, so I'm going to give you 15 minutes, and these are the 4 questions that I would like you to do. There's also in yours, there's a circle in the center, and what's your final takeaway, meaning after you've done all this research, what do you get from this? So you're going to ask, how does fumotoxin work? What is fumotoxin to start with? How does it work? What is phosphine gas and what does it do? Why did the 2 youngest and not the older children and parents die? And why was it put in the yard and how was it cleaned up? And anything else that you can come up with that. I'm going to give you 15 minutes. Research, do your best, and we'll see you back in 15 minutes. Okay, let's come back. What did you find out? What is fumotoxin? Say it loud. It's a fumigant, okay? Okay. Pesticide, yeah, it's used to kill. Okay, so what is phosphine gas and what does it do? Yes?
It's a toxic gas and attacks the central nervous system.
Good. Toxic gas that attacks the central nervous system. So why the 2 youngest and not the older children? Why did they die and not the older children? Do we have any ideas? Yes? Children are more sensitive, okay. Okay, they're smaller, so actually because they're smaller, they were closer to the ground. Phosphine gas is heavy, it goes towards the ground. And their smaller body size had more intake of gas because they breathed faster. And because they breathed faster, they had more phosphine gas that actually got into them because they were in more concentrated area. Okay, so what did the mom and dad think it was to start with? Carbon monoxide or the flu? Because the mom had taken the 2 youngest to the doctor, thinking it was the flu or some kind of cold. And the second time she took him to the doctor, they life flighted the youngest down to primaries, where she died really quickly after, and then the 4-year-old was short to follow after that. So, whose fault was it? Was it all his fault? You guys are almost 18, you're almost adults, and you're going to be responsible for the people that on property that you own. You're going to be responsible for anything that happens on that property. So actually the mom and dad were actually responsible also. Why would I say that? That's so cruel. Why would they kill their own kids? Whenever you have something done in your house, you need to make sure you understand what's being done. And it took you how long to find all this information out? 15 minutes. Okay, was this the first one of these things that had happened with fumotoxin? So if the dad or mom had taken 15 minutes and just put in fumotoxin to a Google search, would they have found what you found? Even though it wasn't that what happened to them? Yeah. So as you go out and you become adults, you are responsible for what's going on around you, even if you have a supposed expert that tells you something. Don't believe everything you hear. Don't believe everything on the internet. Go to more than one source, right? Make sure you're hearing the same things. So if the exterminator came and said, we want to do fumotoxin to get rid of the voles, mom and dad should have asked right up top, what is fumotoxin? What's it going to do? How is it going to affect my kids? And then I still wouldn't take their answer as being right. I would take that 10 to 15 minutes and research it. Okay, so what we're doing in this unit is we're going into something that I think you're going to use more daily, day to day, than a lot of the stuff that we touch in chemistry. But this is stuff that you're actually going to use. So once they found out there was a problem, how did they clean up the yard? What did they do? Yeah. They dug it up and mixed it with water. So mom and dad were worried about these little tunnels that the voles were making. What are voles? They're sort of like field mice, but they're a little bigger. Okay. They're worried about these little tunnels. Well, now they have the whole yard dug up, right? And they've lost 2 kids. They put it with water, but they also evacuated the neighborhood. Why would they do that? And they were in full hazmat suits. If you looked at any of the pictures, they were in full hazmat suits, head to toe. Because of the phosphine gas. What else did they do once they mixed it? That phosphine gas is still around. What'd they do? Anybody read that? They brought in big fans to blow it away. They really did. Why would they do that? Because in small quantities, phosphine gas is not harmful. But in large quantities it is. And right near that house, there was a little shallow area. And if they would have just let the phosphine gas react, or the fumotoxin reacts and make the phosphine gas, that phosphine gas would have stayed in that little hollow. And anybody that went in, animal, human, whatever, would have been affected. But by blowing it away, they dispersed it, made it lower concentration, and was able to take care of it. This is a really sad story, and it's not the first that has to do with gases. And so I want to make sure that by the end of this unit, you are very, very familiar with everything that goes on with gases, that you are consumer smart, which means you can take 15 minutes and do some research if somebody says something and you just want to make sure that you can take care of it. Okay, so let's go on and talk about some things. These are some things that we've already talked about. But who can remember what 2 elements on the periodic table are both liquid at room temperature? Yes? Mercury and bromine, you're right. Bromine is a red-brown liquid at room temperature, and it is corrosive and causes serious problems. It is one of our diatomics. It hangs around in pairs. And the other one is mercury. Mercury is that silver, also known as quicksilver, and it also causes health problems. Okay, what are the gases at room temperature? Who can remember these? Noble gases, good. And oxygen, chlorine, nitrogen, Fluorine. One more. Hydrogen. Okay, so if we look at this lovely chart right here, the yellow are our gases, and the blue are our liquids. What are the whites? Solid. So most of the periodic table, most of the elements at room temperature are solid. And if we know just the liquids and the gases, then we know everything else is solid. Noble gases are easy, right? Because they say gases. So I know that last column is definitely gas. And then if I just remember, oh, nitrogen, oxygen, and fluorine, and chlorine are gases, and hydrogen's a gas. Okay? So let's talk about what are 4 physical properties as we're looking at distinguishing between solids, liquids, and gases that we need to worry about. The first one is density. If density is high, we've got a solid. If we go a little bit below that high of a solid, then we get a liquid. And then if we go really low density, that is gases, because gases have lots of space between them. The next thing we want to look at is shape. A solid, we know its shape. It's a definite shape. This desk is a definite shape. The chair is a definite shape. They're solids. Liquid is indefinite. It takes whatever container we put it in. If we have 50 milliliters of water and I put it in a beaker, I could put it in a volumetric flask. I could put it, every time it will take and fill whatever 50 milliliters would fill. Okay? The difference between liquid and gas is gas will not only fill that 50 milliliter beaker, but unless I put a top on it, it will come up the top and it will disperse. So it will take the shape of a container and fill it. It won't just take the shape of the container like liquid, but it will fill that container. Next thing we need to worry about is compressibility. How well can I compress something? A solid, this desk, I can't really compress it a lot. Okay? So compressibility for a solid is small. For a liquid is a little greater than a solid, but not much. And we ought to be grateful for that, because as we use brake fluid in our cars, we want to make sure to bleed it out so there's no gas in there, because we want to be able to, when we step on the brakes, be able to push that liquid to close the calipers and make our brakes stop the car. If there's any gas in there, then that liquid won't push those calipers to stop, and we have problems, because gas has a very large compressibility. The last one is what we call thermal expansion. Thermal expansion is how does heat affect it. Okay? Solid, if I heat up this desk, it's not going to all of a sudden blow up like a marshmallow. It's just going to get warm. Okay? It'll expand a little bit, but not very much. If I take liquid and heat it up, it tends to get a little bit more excited, and sometimes it will grow a little bit, but not very much. However, if I take gases and I heat them up, then they get really, really excited. So this bottom one, if I took a balloon and I put it into the freezer, it would slow down the gas, and the balloon actually would shrink. If I take that balloon and I put it out in a hot day, it'll actually grow from what it would be at normal temperature. So it has the ability to expand. So let's look at this really quickly. This is going back to our density equation. Who remembers what our density equation is? Yes. Good. Density equals mass divided by volume. Remember, if you're in love, oops, okay, you always get your heart broke. Not always, but you know, high school you do. Okay, so doing this really quickly, mass and density. So basically on this one, what I'm going to do is I'm going to switch these two places. In other words, I'm going to times both sides of the equation by volume. I'm going to divide both sides of the equation by density. And when I do that, I'm going to get volume is equal to mass divided by density. Okay, so basically volume and density just traded places. When I do that, I can put in 125 grams divided by 1.03 grams per milliliter. At this point, grams will cancel out, and I will get milliliters, because 1 over 1 over milliliter is a milliliter. When I take and divide this, it's going to be a little less than 125, right? Because I'm dividing by a little more than 1. So go ahead and grab your calculators out, because we are going to be using them today and for the next bit of the unit. I'll get my calculators out next time for sure, but I forgot to get them out today. Sorry for those that need to borrow mine. Okay, so those that have got a calculator, let's do that really quickly. 125 divided by 1.03. 120 what? 121. Okay, so that's my new volume. Now, this next one, we're going to also use the density equation, but if you'll notice, it says copper metal has a density of this, so density is equal to here at 20 degrees. Density is equal to this at 100 degrees. And we're supposed to calculate the change in volume that occurs with, by the way, this is supposed to be a G. So just erase that centimeter square and make that a G. 10 grams of copper is heated from 20 to 100 degrees. So on this one, I'm actually going to find the volume at 20 degrees, and I'm going to find the volume at 100 degrees and see how it's different. So I'm going to use that same equation right here, and I'm going to do it for 20 degrees. So I'm going to look for the volume at 20 degrees when I take 10.0 grams and divide it by 8.92 grams per centimeter cubed. Grams are going to go out, and I'll be left with centimeters cubed. The second one, I'm going to do volume at 100 degrees. The mass does not change, but the density did. 8.83 grams per centimeter cubed. This time, my grams are canceling out and I get centimeters cubed. Let's get the answer on both of these to 4 significant figures, or 5 even, because I'm not going to get the final answer, and I'm going to be subtracting them. So I want to make sure I have enough that it makes some sense. If anybody's got the top one, let me know. Should be able to do these on the phone if you don't have a calculator too. These are fairly simple. Have an answer? 1.121 for the top one. Anybody got the bottom one? Ten divided by 8.83. Okay, so to define the difference, all I'm going to do is take that 1.132 minus 1.121, and I'll get 110, and that right there, centimeters cubed, is how much it has expanded, going from 20 degrees to 100 degrees, which isn't a lot, but it's enough that I can measure it. Okay? All right, let's go on. We're going to talk about the kinetic theory. And the kinetic theory is all about how gases react and how they collide with each other and how they collide with the walls of things and what's going to happen there. Bromine as a gas still stays as a diatomic. So all of our diatomics on here, Braunhilfe, are going to stay as diatomics. Phosphorus and sulfur, P4S8. All the rest on the periodic table, like helium, would just be He, would just be 1. But the diatomics stay together. So I'm going to go through the postulates of the kinetic theory. Don't write anything down yet because I'll give you a shortened version. But I want you to see what the postulates really are because I'm going to give you an easy way to remember them. So first of all, and I'm going to read them pretty fast, gases consist of tiny particles, atoms and molecules. Number 2, these particles are so small compared with the distance between them that the volume size of the individual particles can be assumed to be negligible or 0. Number 3, the particles are in constant random motion colliding with the walls of the container. These collisions with the walls cause the pressure exerted by the gases. Number 4, particles are assumed to not attract or repel each other. Number 5, the average kinetic energy of the gaseous particles is directly proportional to the Kelvin temperature of the gas. Okay, that's a bunch of blah. So now I'm going to give you an easy way to remember it. There are 5 rules. Usually kids under 5 are called toddlers, right? So we're going to call them toddler rules. We're going to go one at a time. Number 1, particles in an ideal. So this is all, everybody thinks of toddlers as being ideal. So this is, you got to remember these are ideal. Okay, they have no volume. You can hold them. You don't have to pay for a ticket for them to see stuff. You can hold them in your lap. So they have no volume. Number 2, they have elastic collisions. If you've ever watched a toddler learn to walk, as long as nobody's watching them, when they fall down, they just get right back up. They bump into a wall, they just keep going. But if somebody's watching them, what happens? They watch your face to see, oh, how am I supposed to react? If you go, then they go, right? So they have elastic collisions. Number 3, they move in constant straight line motion. That's because they like, oh, this is cool, I'm going to get this. And as they just about get there, mom takes it away and they go, and then they find something else and they go for it, right? So they are attracted to one thing and they go straight line motion to get it as fast as they can before mom takes it away. The 4th thing, they don't attract or repel each other. Okay, they don't care what you look like. They really don't care what's going on. They just want to have a friend. So I'm going to tell you a couple stories from when my kids were little that sort of illustrate this point. Really embarrassing for me, but I'll give you the point. So my kids didn't know very many people of color when we were young. And we went to the store and there was a black lady next to us in line. And my daughter goes, Mommy, how come she didn't take a bath? Oh, no. And so then we had to have a conversation that some people have different color skin and it's okay, you know. But this person had told her and she was really good with her. And, you know, she says, oh, have you never met anybody like my color? She says, it doesn't wash off. You know, she was really cute with her. But I sort of, okay, you know, she's just seeing what's wrong around her, seeing what's different about everybody. Didn't attract or repel her. She just asked a question. A couple times later, going to the grocery store, I just loved taking her to the grocery store. It was so much fun. There was a guy there that, to me, looked scary. He had tattoos from head to toe. He had gauges and nose piercing and piercings everywhere. And to me, he looked scary. She just walked up to him and said, didn't your mommy tell you not to write on your skin? Okay, great. She didn't see him as scary. She just saw him as somebody else. And didn't your mommy tell you that? Because your mommy should have told you that, you know. Yeah, it was a very interesting, he was really cute. He says, well, she did. She did. I don't remember what else she said. That just stuck in my head. I'm like, oh. But they're not attracted or repelled by anybody. 5-year-old and less. They want to be your friend. They want a friend to play with, right? Okay, so 5. Number 5. They have a direct kinetic energy, or amount of energy directly related in Kelvin to the temperature outside. So this is how I remember this. So if toddler, 5 or less, think 5 or less, if it's warm outside, I want to go to the playground. I want to go to the park. I want to play in the sand. I want to be outside. I want to chase that butterfly. I want to. When it's cold outside, they go outside maybe for a little bit, and then they come back in. I want my blanket. Right? When they're cold, okay? So this is how I remember it. Their energy is directly related to the temperature outside, okay? All right, so what are the 5? Don't look down. Don't look down. 5, what are they? No volume. What else? Don't attract or repel. Elastic collisions. Energy is related to temperature. Straight line, random motion, right. Okay, so really quickly, you got the 5 Tyler rules, right? In your head now. They're not exactly like they were written to start with, but you've got the 5 ideas, right? Okay, so get real. You then become teenagers. And you're not ideal anymore. What changed? What changed? Not everything. There's 3 things we're going to put down. I know it only has 2 places, but we're going to put 3. What things changed? Think of your 5 toddler rules. What of those toddler rules changed? You attract and repel. Yes. So there are people you like and there are people you do not like, right? So you attract and repel. What else? You do not have elastic collisions. You learned this in driver's ed, right? Okay. What else? There's one more. Your energy is still related to outside. Volume. I have to pay for my seat now, right? When I go places, I got to pay for my seat. So we've got three things that we worry about in real gases. Okay? So I have my own volume. I'm attracted and repelled by people. And I have learned through driver's ed that collisions are not elastic. There's a consequence for running my car into a wall or another car, right? Okay, so here's the mom in me. Teenager, you're real, but toddlers were so ideal. How can I get you more like the toddler? At what point are teenagers more ideal than other points? When you leave. All right, what time of the year are you more ideal than others? Summer, why? Because you're outside. So gases behave more ideal when it's summertime. Low pressure. I don't have to worry about tests. I don't have to worry about quizzes. I don't have to worry about homework. I've got low pressure, right? And I've got high temperatures. So I can play in the water, right? And one more thing. There's always three. I don't have to be with Mr. Blah, blah, blah's seating chart next to so-and-so that I do not like. I can choose who I hang with. So I'm in non-polar situations. Okay? So those are the summer, I think of them the summer exceptions, or making real gases more ideal in the summertime. All right, let's see how many you remember. Okay, how are teenagers different? Volume. Attract and repel. Collisions are not elastic. Okay, real teenagers, how do I make you more ideal? High temperature. Low pressure. Non-polar situations. I can hang with who I want. Okay, so let's do some definitions. Kinetic energy is the energy of motion. Okay, kinetic energy is 1/2 mass times velocity. That's not volume, that's velocity. Lowercase v is velocity squared. What has the most effect on kinetic energy, mass or velocity? Velocity, because it's squared. Okay, so that has the most effect. So the faster I go, the more kinetic energy I have. Potential energy is just that. It's potential. It's what I might have, right? It's what's inside me. It's because of I'm hanging together, okay? It's what's holding me together. These two go together. Cohesive forces are the attractive forces between particles, and it is associated with kinetic energy, so it's what holds it together. Disruptive forces go with kinetic energy, and this is the force that is resulting because of a particle in motion. Okay, so it's associated with kinetic energy. What things am I doing to disrupt this beautiful, happy state of potential energy? Well, I started the ball rolling. Because I started the ball rolling, I've got velocity, I've got friction, I've got all these other things going on. Okay? No, there's a lot of words there to write down. I'll wait for the bob and weave to stop at the back. Then I'll know you guys are about done. Everybody have a good break? No, I didn't want to come back. I had such a fun break. I had lots of fun. Huh? He had a good break until Friday last week. And then he really had a break. He tore 2 ligaments. Okay, here we go. So, what was the equation for kinetic energy? Do not look down at your notes. Ke equals. I forgot I already had it up there. I was like, why am I writing it? Kinetic energy equals 1/2 mass times velocity. Remember to remind yourself the lowercase v is velocity, okay, because we're going to be working with capital V, and that's going to be volume. So we're going to look at this picture that's in your notes right here, and we're going to identify what's going on, what kind of energy is going on at different places. So as this boy throws the ball up, and it comes right back down to where he is. It sort of shows an arc here, but I wanted to show the arc so you could see what was going on. So if going up, what kind of energy do I have when it's going up? Kinetic energy. And in that kinetic energy, I have disruptive forces, right? Because it's moving, it's in motion. When I get to the top here, right before it goes back down, it sort of like holds for a minute. What's happening there? Potential energy, and we have a potential energy, we have the cohesive forces that are in play there. Then as we come back down, what kind of energy do we have? Again, kinetic. So kinetic is the energy of motion. And here again, we're going to have disruptive forces. So we can sort of label a diagram and be able to see at a diagram what's happening and what part of the diagram is what kind of energy. As we go on here, let's actually see what's going to happen here. Say this guy right here, he is my 180-pound linebacker or whatever, halfback, there we go, running at a speed. I really need his mass in kilograms, so I'm going to put it up there in kilograms. That's supposed to be 81.8. And then he is running this way at 8.0 meters per second. This guy, even though he doesn't look as fatter, he's actually fatter. He's 260 pounds, and he weighs 118.2 kilograms, but he's only running this way at 3.0 meters per second. I want to know which one's going to run over the other one and push them out of the way, kind of thing. Okay? So, which one has more kinetic energy? Well, I'm going to find the kinetic energy for a 180-pound person first. Remember, kinetic energy equals 1/2 mass times velocity squared. So if I go 1/2 mass, and I'm going to use kilograms because I want to keep it all metric, and then I do the velocity, and I square it, a kilogram meters squared divided by seconds squared is equal to what we call a joule. So we're going to put it in joules. So if I put that in my calculator, 8 squared is 64. 64 times 81.8, get an answer, divide it by 2. What was my final answer? It's like 1,000 something, or 2,000, I can't remember. $2,617 joules. Okay, that's a pretty amount. That's a pretty good amount of energy. Let's see what this 260-pound person has. So 260 pounds, we're still going to use a kinetic energy equation. 1/2, 118.2 kilograms times by 3.0 meters per second. We're going to square that, and we're going to get an answer here in joules. So 3 squared is 9. 9 times 118.2, get an answer. Divide by 2, what do we get? 531? Okay, 532 if we round. Okay, so this one right here has a lot more energy. Even though he's lighter, because he's moving faster, the velocity actually causes us to have more energy. So this guy is going to push this guy back. Okay? All right, and we could actually subtract it and find out there is about 2,000, what? My brain just left. 17, so 83 joules that he has above the other one. Did I do that right in my head? It's an 85. See, I told you I didn't. Tried to do that in my head and didn't work very well. All right, came close. All right, so now we're going to do it without so much math. Okay, so we've got to think about it a little bit more. Which would have a greater kinetic energy? Hydrogen molecules. Now I've got to think about this. Hydrogen is H2, so the mass is going to be 2 times the mass of hydrogen, which will give me 2.016. Everybody okay with that? In grams. We okay? Okay, traveling at a velocity, so velocity for this is 2 times some velocity. So I'm going to have a variable in there. Okay, then I'm going to take helium, and helium's over here, He, and its mass is equal to 4.0026 grams, and I don't have to do anything with it because it doesn't hang around in pairs. It's not a diatomic. And it says it's going to travel with a velocity equal to v. Okay, well, I know kinetic energy, so I'm going to do this kinetic energy first. Kinetic energy over here is 1/2 mass times velocity, so 1/2 times 2.016 grams times 2v squared. So that's going to be 1/2 2.016 grams 4v squared. This will cancel with that, leaving a 2. That means 4.032 v squared. Okay, that's that one. Let's try this other one. So I really didn't need a calculator because I could do it without it, right? On this one over here, we're going to have kinetic energy is equal to 1/2 times 4.0026 grams times v squared. Okay, well, this will go into this and leave me 2.01013 and v squared. So that's the answer for that one. Well, the v's are the same, so I could just look at that and cancel those out. Well, this means this one has a greater kinetic energy, right? I didn't need to know what v was. Okay. Everybody okay with what I just did? Understand how to do it? Okay. So we've talked about states of matter since you were little. You know about solid. You know about liquid. You know about gas. What we haven't added is plasma. Plasma is a very high energy gas that has been split into ions. So it has a positive and negative charge. Okay, and we're just going to add that to your list of solid, liquid, gas, then plasma. Okay, so you know what plasma is. And plasma has more energy than gas. Okay, because we need to rip those pieces apart and make them into ions. Okay, so let's talk about this. Now back to your 5 toddler rules. Remember, I'm going to keep bugging you about those 5 toddler rules. You're going to tell me which of the 5 toddler rules has to do with each of these. So let's look at the first one. Gases have low density. What toddler rule has to do with that? Gases have low density. Has no volume. Right. Okay, so they have low density because they have no volume. There's nothing there. Okay, how about the next one? A gas always exerts uniform pressure on all walls of its container. Which toddler rule? Okay, it has elastic collisions. There's another one too. Constant random straight line motion. Good. Okay, next one. Solid liquids and gases expand when heated. Which toddler rule does that come to? 5, which is what? Kinetic energy is directly related to the temperature. Okay, good. All right, so let's go on to a little bit more. So that was all that looking there. The following statements are best associated with solid, liquid, or gaseous states of matter. So I'm going to have you do solid like this. That's an S. L for liquid. And gases this way, G in sign language. So I want you to show me which you think this is. Okay, so the first one. Temperature changes influence the volume of this state substantially. Solid, liquid, or gas? Show me. So solid, liquid, or gas? It's gas. It's gas. Okay, in this state, constituent particles are less free to move about than any other state. Less free. Less free to move about. Should be giving me a fist. Solid. Solid. Okay. Pressure changes influence the volume of the state more than any of the other 2 states. So pressure changes affect this one more. Should be showing me gas. Gas. Okay, this state is characterized by an indefinite shape and a low density. Indefinite shape and low density. Again, that's gas. Good. Okay, I'm going to pass through this really fast. Some of the answers are wrong because I did a copy and paste, and yeah. Okay, so let's just review really quickly while we're talking about gases. What are some of the characteristics? A gas will expand to fill a container. That's because of random motion, no attraction. So there's 2 of the 5 kinetic rules there. Gases are like fluids, like liquids. That's because of the not attracted or repelled. Okay. Gases have very low density. That's because they have no volume, lots of empty space. Okay. So as we're looking at gases, some other characteristics. Gases can be compressed. Okay, they can be compressed. Because they have no volume and lots of empty space, they can be compressed and made to put in little spaces. This is another thing that we need to be worried about right here, and you can write that into your notes somewhere. We need to know the difference between diffusion and effusion. Diffusion is if I sprayed a thing of Lysol over here, it would diffuse through the room. Eventually, everybody will be able to smell it. Effusion is when I have, for instance, gas in a pipe and there's a hole. And that gas comes through that little teeny hole, it effuses through that hole. Then it will diffuse through the room. So natural gas really doesn't have a smell. That's why they put a sulfur compound in it. And that sulfur compound is what you relate to natural gas, the smell of natural gas. So it would effuse through the hole and diffuse through the room. Does that make sense? So effuse is a small hole, and diffuse is moving throughout the room. Okay? All right. That's because of their random straight line motion. So let's talk about what is pressure. This is on your notes again. So pressure is force divided by area. That's what pressure is. What causes pressure? Collisions of gas particles with each other, with the walls of the container. Those create pressure. So for instance, when you get in a crash, pressure is created because of all the things you have to do afterwards. Okay? Up here are some different pressures that we need to be able to go back and forth between. These are all equal to each other. So we can set up a dimensional analysis and use these to make different fractions depending on what we want to get rid of and what we want to go to. So 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters mercury. Now, torr was actually the name of the guy that measured in millimeters mercury, so sometimes they use torr and millimeters mercury back and forth. It's the same. 101.3 kilopascals, 29.92 inches mercury, 14.7 pounds per square inch, or 1.013 bar. And you'll notice bar and kilopascals are off by 100 times 100. They're the exact same number, but it's off by 100. So we're going to be using these. If you didn't get those copied down, there at the bottom right here. We're going to be using these to go from one unit to another. So I'm going to set up the first 2, and then I will let you do the others. Okay? So a weather report on TV says that the barometer is at 28.6 inches of mercury. And we need to find out what it is in all these others. So I always start with what I'm given, 28.6 inches mercury, and I'm going to write it on top because I know the back roll does the bob and weave if I write too low. Okay? Since I want to get rid of inches mercury, I can look right here, and there's 29.92, so I put it on the bottom, inches mercury in my conversion stuff. And since I want to go to atmospheres, I look right here, and there's 1 atmosphere. So I'm just making a fraction here that equals 1. At this point, inches mercury and inches mercury would cancel out. I would take 28.6, divide it by 29.92, and get an answer to 3 significant figures. So let's go ahead and do that. Let's see what we get. Okay. What do we get? Say brave. Be brave. 0.956 atm. That's how many atmospheres I've got. Okay, let's do the next one. We want to go to torr, but we still have the 28.6 inches of mercury. So I'm still going to use the 29.92 inches of mercury because I want to get rid of it on the bottom. But this time I want to go to torr. So this time I'm using the 760 torr on the top. Inches mercury will still cancel out. What do we get here? We get what? 726 torr. Now, the nice thing is, torr and millimeters mercury are the same, right? So we've already got the answer for this one, 726 millimeters mercury. They're interchangeable. Okay, I want you to do the other three. I'm going to choose people to put it up. Dun, dun, dun. Will you put up PSI? Will you put up bars? And will you put up KPA? And you can choose your color. Computer, you might want to start putting it away real quickly, and while these guys are getting the answers up. Make sure you plug it in and tuck the cord in for me, please. And then let's do a double check and make sure we got these answers right.
Oh my gosh, this is me.
You're just right there. You should be able to reach it. You can do it. Okay, let's check these. How do we do? On C, did everybody get 14.1 psi? Woohoo! On D, did we get 0.968 bars? Yes. And on F, did we get 96.8 kilopascals? Woo! Pretty easy. Okay, we're going to be using this a lot. So this is something you want to keep near you. It might be something you want to put on your card. Okay, unless you've got it memorized. And we will start, see if I got all the answers you guys did, which is good. We're going to start here with kinetic theory and the gas laws next time. Okay, please make sure that you wear closed-toed shoes. If you wear contacts, I will remind you again next time to please make sure you wear the full goggle. Okay, and we will start off next time. We'll have 2 labs. We're going to start off with some lecture, and then we'll go to the labs. No, 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 no. We're doing it in the hood, too, so. The hood. The hood. Have a great day, guys. That thing that sucks up air. It's where you grew up. In the hood. Oh, I need to shut that off. I forgot to stop it.